In this video, I want to do one more example of constructing, of doing a hypothesis test for a difference of two means using R. And so we just did the slide previously to this, just walked through how we could do it with the North Carolina birth data set. So here we're going to stick with the theme of newborns, and there's a data set from the resample library called Girls2004, which, similar to the North Carolina data set, contains samples of births that were in Wyoming and Alaska in this case. And they recorded things similar to the previous one, like what was the birth weight in grams, what was the gestation period, and that was being measured in weeks, and as well as whether or not the parent used tobacco or the birth mother used tobacco or not. And what we want to test here, what the researchers want to determine, we can see from this statement over here, whether the mean gestation period in Alaska, births in Alaska, was was greater than the mean gestation period for the births in Wyoming. So we could state this in various ways, but however we state it, the null hypothesis should be claiming that there is no difference between these two. So for example, the mean gestation period of the births of all births in Alaska minus the mean gestation period for all births in Wyoming in 2004 was 0. We could say that they are equal to each other. I could say that the mu Wyoming minus mu Alaska is 0 as well. So we can do this in different ways as long as it's consistent. So the alternative now is we do have a direction here, which is we think Alaska, we're claiming that the gestation period in Alaska is greater than the gestation period in Wyoming. So in this case, that would mean that that difference should be positive if the mean gestation period in Alaska is greater than that in Wyoming. And so now we want to use R to calculate this test statistic. We want to use the t.test feature built into R. So in this case, that would look like, recall, we're going to say t.test, and then the very first thing we enter is what is the numeric variable we're testing. And here it's the gestation periods. And then we put a tilde, which is what's over here, and then we say, how are we going to split up the sample into groups? And that's going to be based on state. So we have two states in this data set, Alaska and Wyoming. And then we need to tell R where these variables, where this data lives. And this is now in the data set Girls 2004. And then we need to indicate what is the direction in our alternative hypothesis, and that is now greater. So here we can hit greater. I believe you can just enter G, and it would read that as well. So that's how we would want to enter this in R. And then when we do that, here's the output that we get. And this tells us, okay, we're doing this two-sample t-test using Welch's approximation for the degrees of freedom. And so we can see down here that these are the degrees of freedom that we get from Welch's approximation. Over here is our test statistic, so that's about 2.1568. And it also calculates the p-value for us all in one shot over there. And so if we were doing a test, say at a 1% significance level, then what would our conclusion be? Well, we've got a p-value of 0.0716, and we can see here that p-value happens to be just slightly greater than the significance level, which in this case was chosen as 1%. So if we were using a 1% significance level in this test, then we would fail to reject. This is not a statistically significant result at the 1% level. So here we would fail to reject the null hypothesis. And the test is inconclusive. So we can't claim anything about the differences in these gestation periods for the babies born in Wyoming versus Alaska in 2004. Okay, so that's how we can do this with all in R when we've got the raw data set with all of our individual observations. So just be sure you understand that first comes the numeric variable, and then comes the categorical variable, and we may need to specify a direction. And in this case, we did a 1% significance level. And let me just say that by default, when it does these tests, it uses a 5% significance level, which is why we see some information about a 95% confidence interval. We don't really need to bother changing the confidence level here because really all we care about is the p-value, and then we need to do this comparison on our own. So the p-value is independent of the significance level that's chosen. The p-value depends on our sample. But then the decision that we make does depend on the significance level that's chosen. And as well, since we had a one-sided test here, we really wouldn't interpret this information in the 95% confidence interval in a meaningful way like we did in the previous example where we had a two-tailed test.